right, welcome back. We are here with episode 7 of Database Deep Dive. Today we've got a really amazing topic. We're going to be diving into graph databases with Amazon Neptune. But first, we've got an amazing guest with us here, Brad Beebe.
BB,
yeah. All right, so Brad, why don't you tell us a little bit about what you do here and your work with the Neptune team?
Yeah, sure. So my role here is I lead product and engineering for Amazon Neptune. And I've been involved with the service since before its general availability, which was in May of last year. And in general, I've been in the graph space for quite a long time. And so it's been sort of exciting to see graphs and how customers use graphs evolve over the years. And I think that this is a very interesting time to be in graph because we're really starting to see customers really see how to use relationships and how to use relationships to build new applications and create new things. And the performance of graph databases is now there where you really can think about using these things for applications at a broad scale that, whereas before you might have limitations or pieces. So.
Awesome. And I've hoodwinked my co-host there at the end of the aisle. Randall, back with us again.
Unfortunately, you're stuck with me.
So yeah, we've got an awesome show lined up for you today. Brad has a lot that we're going to talk about with graph databases, but where do we start here?
Well, I think what we should say is we should set this in the context of the various other databases that we've talked about. So for those of you who are joining on the stream live, we've been doing this series for a couple episodes now, and we've been taking a lot of questions from the audience, and we've also been taking questions from email. All those questions via the email, we're going to get to those in the last maybe 15 minutes of the show here. But for the first portion of this show, what we're going to do is we're going to talk about graph databases and talk about Amazon Neptune. But any questions that you have, Brad is the person. He is the expert. This is your chance to stump the experts, So please send your questions in chat and send them over email. We'll be monitoring those throughout the course of this episode. With that said, maybe we can kind of jump into why we use graph databases.
Yeah, I think the thing to remember about graph is that you really want to use a graph database when you want to make a connection or when the primary thing that you're doing in your application is traversing relationships. And that's really when you kind of want to focus on a graph, because a graph database optimizes storage and query processing to be able to traverse those relationships very quickly and easily.
Yeah, and so when I think graph, I think, and querying graphs, I think about these really complex statements that I would need to write in SQL or in NoSQL and query a bunch of data and filter it down. But graphs sort of flip that on its head and say, well, we understand that data exists and is very connected out in the wild for certain instances. What if we could essentially query that in a very efficient way in the same way we think about those relationships, right?
That's right. At the core, a graph is a data model. And it's a data model that consists of nodes and links. And those links make those relationships sort of first-class entities in the data model. So if you think about a relational model or a key value store, you can model those relationships, but you have to denormalize the data or use join tables or other things that I'm sure everybody's familiar with. But you're not referring to those relationships directly. And in a graph model, in a database that supports a graph model, you can refer to them directly and write applications very quickly and easily over them.
Yeah, so for example, in like a relational database, you just, as you get more entities, you just have this exploding sparse data set that just has ones and zeros to represent relationships, but in Neptune, it can do it in a more efficient fashion, for example, right?
Yeah, and many customers use different ways to try and model graphs and non-graph systems. And I think in general, the end result is often the same, is that it's something that you can do, but what you lose is agility and the ability to create new relationships on the fly. And that's really where the power of graphs come from, because graphs allow you to just make relationships between things that you wouldn't have thought of before, maybe systems that weren't ever designed to be related. Excuse me. And so you can do that very easily with the graph database.
Yeah, and so for a lot of people that may not be familiar with graph databases, they hear these things like, my data is connected or these relationships between different points. But what are tangible examples of like data sets that fulfill this sort of dichotomy of nodes, edges, and relationships?
Yeah, well, I think the thing that many people relate to initially is things like social networks, for example. I mean, most folks have some experience with some kind of social networking application. And in that model, the individuals in the network and their connections are sort of fundamentally a graph. And so, that is one example. I think one of the things that, we think about the power of relationships. If you think about a social network and you have maybe 10 people and their connections, that's sort of interesting. But imagine that you have 10,000 or 100,000 or a million or 10 million or a billion relationships. Now you have this pretty rich set of information, and you can traverse it and ask it questions, and it can tell you really interesting things. And so, that's really where we like to think about, from in terms of relationships and relationships at scale for graphs.
And one of the interesting things for me to learn as I was learning about graph databases was that it's not just the nodes that have rich data, it's also the edges that have very rich data associated with them as well. So, the edges can contain complex data in them, and it's not just, the node is not the only object that is able to be queried.
That's right. You can, in a graph model, you can have essentially properties or statements about both edges and nodes. And, the right way to do it really depends on your use case. I mean, sometimes it makes sense to put those kind of attributes onto edges. Sometimes you may want to model them as nodes. It really depends on the questions that you're going to ask. And, like almost every database system, we, recommend start with the question. Mm-hmm. And then, once you understand the questions that you want to ask, a lot of that will drive the data model and how you want to look at things.
So maybe we can step through some of these slides here and see what a social, how we might model these things, kind of walk through some of the vocabulary and walk through some of the use cases, as well as maybe some customer examples.
Yeah, I mean, so the one thing to take away from today is if your question is when should I use a graph database, it's when I have relationships and I want to traverse them, and that's really the core thing to remember, and that's when a graph database is really the right choice. The thing that is just really cool about graphs is how broad the use cases in the application space is. You can go from talking about social networking to helping people find information to protecting your network to understanding how to link healthcare systems to discovering new drugs to making recommendations all in a single day or in some cases an hour. And so it's really exciting to see all of the different places where graph data models are important and they show up. And so these are the 6 that we have here are really the 6 that we really focus on from a product perspective, but there are a broad set of different applications, and I think that's a power of graph. It's also a challenge for a lot of customers to get started, because many of the solutions that people have used successfully, they're maybe a little different than you see as a user of graph, and so you want some help, or you're interested in how do I take something that's been successful and apply it in your own use case.
And I mean, even social networking, that's a pretty broad area. Recommendations is super broad. Knowledge graphs are super broad. So you say that those are the 6 that we focus on, but when I look at these, there's a huge portion of
right. These are really, as you say, these are really broad sets, and even in any one of them, you can find different applications that are of both a different nature in terms of maybe they're interactive access patterns, or maybe they're more analytic access patterns. You can find them that have very different types of data, and so there's a broad diversity of the kinds of use cases and things that you can do there.
Yeah, I mean, even on the topic of life sciences, I think you just mentioned drug discovery, for example.
Sure.
But then also I know that genes exist, the genotype and phenotype exist sort of as a graph relationship, and so understanding what genes are mapping to certain outputs is a huge graph problem, for lack of a better word. And being able to set that up in a graph database enables computation on top of that to be able to make that analysis possible.
Yeah, you can traverse the relationships between the gene expressions. You can ask questions about patterns of them. I mean, and even in healthcare and life sciences, you have these things like looking at genomics, and then you have these things like looking at chemical compounds and protein pathways. But then you also have integrating hospital systems, and how do I make a patient record that's coming from lots of different places look in some way canonicalized so that I can query it easily. And so, every one of these, domains has those kinds of examples that really run the gamut.
Yeah, so the big takeaway here is that graphs are kind of everywhere. We may be used to seeing them, but we may not be used to thinking about them in the graph data set sort of model.
I think that's absolutely right. I think that, the way that we look at graph is that the number of customers that today know they want to use a graph database or are using a graph database is relatively small versus the number of people that have a graph problem or could benefit from processing relationships.
Wonderful. So maybe by watching this show, they'll figure out how they can get started with being able to bridge that gap.
Absolutely.
So if I wanted to, for instance, query recommendations or figure out, what's the Netflix use case, right? Is like, oh, this person watched this movie and this person, how do we recommend other things to people on that? Is that a good kind of graph problem?
Recommendations certainly can be. Sometimes I stay away from recommendation a little bit because there are many ways to make recommendations.
Deep learning.
And some of them are graph-based, and graph can be a great way to do it if the things you want to recommend are based on relationships. But there's lots of other ways that people make recommendations. So it's it is a good graph use case, but it's one that also has other use cases associated with it.
I think that's a great example of how, in the same way, graphs can be applicable in many subject domains. Like even a specific use case, like driving personalizations, can have many different types of technology that can be optimal depending on the situation at hand.
Absolutely, and as you guys, I'm sure you've talked about it before, we really believe that it's kind of looking at what's the right purpose-built solution for which part of your application. So you take your application, you sort of decompose it down, and graph has an important place in that process.
So let's continue on here and see if we can't see a couple examples of this in practice.
Yeah, so you were asking about relationships, and so I have a quick example that's sort of a conceptual one, on a relationship recommendation piece. And so, suppose that, I start with a little bit of a social network. You can see that, Bill knows Alice and Bob here. And then, I'm going to use the Power Graph. I'm going to bring in another data set that I have. So I'm going to bring in some product purchase history. So I can also see that, Dave purchased this product, as did Bill and Bob. And, remember that, one system had my social networks and one system my products. And so I'm building something new that makes relationships between them. And I also have some shared interest information. So I can see that Bob follows sports and Sarah follows sports. And by using a technique that you call triadic closure, which is basically a triangle is the smallest fully connected subgraph in a graph, by finding edges that I can create, relationships I can create to complete triangles, I can do the start of a recommendation engine. So I can, for example, say that Sarah might want to purchase this product because people who also follow sports purchase the product. And again, if you look back to that social side, you can see that there are two people who have a friend in common but don't yet have a relationship. And so again, that would be a candidate for a recommendation example. Now, I don't want you to think that graphs are all about social networks and recommendations, because they're really not. That's just one important use case. And so something that we see quite a lot of is something that's called a knowledge graph. And a knowledge graph uses a graph model to encode information to represent things that you know and how they're related. And then you can use knowledge graphs to help people find things, to help people answer questions. So for example, Amazon Alexa uses Neptune as part of the technology to implement their knowledge graph suites. We have other customers that are building knowledge graphs. And so this is a quick example of a knowledge graph application. And it's taken from the World Wide Web Consortium, or the W3C's sort of prime run knowledge graphs. And we start with a very famous piece of artwork, the Mona Lisa, and where it's located, a very famous museum, the Louvre. And we also have some information about the artist and where it was presented. And again, in that theme of linking information from different sources, we also have some social network and shared interest information. So we can see that Bob is interested in the Mona Lisa, Bob has some friends, there's some biographical information. And again, we'll now add in some reference information. So we know some facts. We know where the Eiffel Tower is located. We have some travel history. We know that where Alice has traveled and that they visited the Eiffel Tower and that the Eiffel Tower is in Paris. And by bringing all these things together and encoding them in a graph form, we can now start to answer more sophisticated questions. So we can say things like, who painted the Mona Lisa? Or what museums should Alice visit while in Paris? Or what other artists have paintings in the Louvre? And so this kind of knowledge graph approach is a really powerful way to do a lot of different things, but it all starts with representing things you know or a domain of information that you care about in a way that you can ask questions over it. And that's fundamentally kind of what we're doing here.
There was I was trying to find this not too long ago. We used to have this data set. I think it was the University of Sheffield or somebody that created it. And it was this huge knowledge graph that was kind of scraped from Wikipedia. And it linked all of those nodes together. And I don't see it in our open data sets anymore. But we do have the software heritage graph data set now, which is,
right.
If you've never seen this before, it's basically version control history from a bunch of different projects, everything from like the Linux kernel to a bunch of stuff on GitHub, and that's a fun little database to play around with, and it's all in S3. But are there any kind of cool open data sets that you know of for knowledge graphs?
I mean, there's quite a lot of them. I think that the place that a lot of customers start in general is you mentioned Wikipedia. There's an effort within Wikipedia called Wikidata. Wikidata manages the structured information that's
right.
Owned by the Wikimedia Foundation. And Wikidata a couple of years ago stood up a Wikidata endpoint, and they have a query service. And so they represent all of this structured data as a graph. You can issue Sparkle queries over it, and you can answer questions with anything that Wikidata knows over it. And so that's something that is a lot of customers use. A lot of them use to bootstrap different knowledge graph informations if it's in sort of a consumer or public domain piece. And it of course it's always fun if you're out and you want to answer a question or you need to settle some sort of dispute between the two individuals. It's an effective way to do that as well.
So if you're skilled at writing Sparkle, you can go and say, okay, well, did this many more references to this?
Yeah, and you should actually, I encourage everyone to check out sort of query.wikidata.org. They have a handy sort of Sparkle editor that you can use to edit queries, and they have a lot of example queries. And so it's quite a nice, easy way for you to explore the Wikidata and also get a sense of what's a knowledge graph and how can a graph representation help you find things and build applications over it.
I think another thing to mention is that obviously there's a large number of great open data sets that are out there, but this isn't particularly difficult to get up and start building your own graph database internally, and you can conglomerate different data sources that you already have from their different database formats, as long as you have some level of continuity between them, such that there's valuable relationships there, right? So a great example here is pieces of art and users and locations. Obviously, not every company has those as their subjects, but with one common thread between the different relationships, you can start to answer these very complex questions or build functionality based on those queries just by using the data you already have.
Yeah, absolutely. And there's different graph data models as well. And one of the things that is a strength of certainly the resource description framework or the RDF model is that it has a very strong sense of identity. And so each piece of information has what looks like a URL, which is actually called an IRI or an internationalized resource identifier to uniquely identify it. So that really facilitates these kinds of use cases where maybe there's publicly available information. You want to build some things on top of it, but having that identity allows you to link between these data sets.
So you can have multiple disparate data sets in different locations and even hosted by different customers, and you can pull them together in the same schema by using that IRI.
Absolutely.
Or is it
IRI?
IRI. Okay.
IRI.
And that's one of the things that I learned. We have a customer, Siemens Corporate Technology, that spoke with me on stage in Berlin.
Yep.
And they talked about how they basically have 140 different canonical sources of truth for all of their different turbines and different things that they manage in the field. And they bring all of that into Neptune in order to query and to do everything from preventative maintenance to supply chain prediction to forecasting for how many new turbines they're going to need to build and stuff like that. And they use those IRIs in order to link all of that kind of commonly referenced information together from all these different data sets. And I hate XML, so working with RDF has never been fun for me, but I do see the value in that kind of format of the semantic definition of what the data should look like.
Yeah, and I was sitting at the back of your talk there. I gave a talk later at the
Yeah,
Berlin
I
Summit,
remember.
And the presenter from Siemens gave a quote that I recall that I've used a number of times. He's like, "I love Graph because it lets me integrate data like crazy." And that's what he set up on the stage at Berlin Summit. And I think that's really true. You know, customers, that's what customers want, is that they're able to innovate because they can make these relationships and integrate the data very easily. And, you know, in terms of the XML side, you know, RDF is a data model. So
Yeah.
there's XML and non-XML serializations as well. So even if you don't like XML, there are some options for you.
I would love to learn about those, because the only ones I've seen have been, like, even the Wikidata one, I'm pretty sure it has this huge XML definition for each article and things like that.
Yeah. It's definitely there. So.
Mostly because I guess this kind of came about in the time of like XSLT and all the maybe like the mid 2003 2004 time frame is when they really started taking off with these kinds of formats of semantic definition of what these things should look like.
Yeah, it was actually a little bit before that.
It was?
It was
Oh.
in the late 90s.
Wow.
They were largely different kinds of metadata management applications. And sort of in the late 90s, the U.S. DARPA, the Defense Advanced Research Project Agency, started something called DAMA, DARPA Agent Markup Language. And then the Europeans had something called OIL, which was the ontology interchange language.
I remember that.
And those sort of came together about 2000 and, you know, became, you know, what was now called OWL, the ontology web language, and that was built on the data model for the resource description framework. So, you know, a lot of the legacy of some of that side of the stack, you know, dates back to there, but they're really thinking about, you know, at that time was XML was all the rage, and so, you know, there were lots of serializations there. But I think we've learned that XML could be verbose, and
Yes.
we've moved beyond that in many ways.
I do this every episode, and I'm so sorry, but I want to draw an allusion back to the 1990 Oracle, the 1990 Postgres design paper, in which they originally laid out the idea of how graph models could be represented in relational databases. And I'm just going to go ahead and say again, the people who made Postgres, Stonebreaker, and all those other people were way ahead of time. Like they were tuned in, they knew what was going to happen. So Postgres ++. Just a general comment.
But yeah, I mean, so I think that's a great like segue into talking a little bit about the interface for interacting with this, right? So that's a ton on like the serialization and how that data is stored semantically, and how ultimately we converged on some sort of standard, and RDF is now what we work with today. But then how you choose to query that is an entirely different ballgame, right? There are different optimizations that you may want to make with respect to that querying. So, you know, like, what are examples of customers that are using this? Or, yeah.
Yeah, I
Some
actually
standards.
want to go back to the graph model question a little bit, because I think
Yeah.
it's really important. And so there's really there's two leading models for graph. We talked a little bit about RDF today, but the other model is something called property graph. And in fact, you know, in some cases, many more customers may be familiar with property graph as a graph model. And they both represent graphs, right? I think, you know, property graphs are typically, people think of nodes and edges, and nodes and edges both have properties. And then, you know, in RDF graphs, we've talked extensively, they sort of have this history and resource description, so they have these IRIs and other things. But, you know, what in general we find is that developers tend to resonate towards property graph. You know, if you're thinking about coming from a relational database, thinking about rows and tables, and then going to nodes and edges and their properties, can be a relatively straightforward kind of transition. And customers that are really thinking about their data models, and so your information architects, you know, really tend to resonate, you know, to the RDF side, because it has these standards and ways to represent different information models. And I think that what we see increasingly is that, you know, really customers want both. You know, customers want the power of being able to relate data together, and they want to be able to traverse relationships. And so they really want graph is what they want. Is that they don't necessarily want property graph or their RDF graphs. They want to be able to build graph applications, you know, over their data, you know, quickly and easily. So we increasingly see customers that, you know, are really interested in in both models. And, to kind of make it graph for me. Don't make it RDF. Don't make it property graph. Give me the best of both of them. And
So let me query using the model that matches the data.
yeah, I mean, choose the best model for your application. Sometimes that's property graph. Sometimes that's RDF. But have the power to choose, and then, in many cases, customers also want to have the power to go between them.
Okay, great.
I think that's kind of like one of the biggest themes we found with the show is that like it's not that you can't do it in one form. You can do it in both typically, but you want to optimize again here for your use case, and a lot of times that comes down to what is the query that your developer is going to be writing. And sometimes you may have different teams or different developers that need to query that graph in different ways.
Right, and sometimes you also have more of a system approach to it as well. So you might have, like for example, in the Siemens use case that they presented at the Berlin Summit, they had lots of different sources of data. They were using the RDF model to bring them together, but then when they want people to build applications against that, often they want the property graph model. And so how do you take the power of doing all that alignment and doing all the hard work about figuring out what this means and what schema and how do I translate that to where, and then take it in a form that people can really build applications over too very easily.
And so the kicker here is that Neptune enables you to use both.
So Neptune does support both. So Neptune supports both the property graph model and the RDF model. And so it gives you really the choice of choosing which one is best for you. Today, Neptune does not support interoperability between them. So you can use Neptune for either, but your data is essentially separated in between them. But we're very interested in hearing kind of use cases and where customers want to go between them and want to do both. And it's something that we do see, as I mentioned, our customers wanting to do.
Wonderful. So maybe it'd be really valuable to take a look at what these queries or these relationships look like in RDF, or in what these physical encoded relationships look like between objects.
Yeah, so let me start with a property graph example. And this is taken from a Practical Guide to Gremlin, which, if you haven't seen it, is an open source Apache 2 licensed book about using Gremlin. For full disclosure, it's is written by Kelvin Lawrence, who's now with us at AWS. And so he's on our customer advisory team. But he's really put together a very good place to get started with the Gremlin language and property graphs. And the data model that he's chosen, probably not unlike you guys because he likes to spend time in airplanes, is really looking at airports, routes, and distances between them. And so the whole book takes place around this air routes data set that he's created, and it makes publicly available. And so this is an example of a graph that we see, and we're basically looking at, on one hand, in the middle you can see the graph. The things that are the ovals represent your nodes, and the arcs between them represent your edges. If you look on the left, you can see your node or vertex properties, and so these are data attributes that are about that node. So you can see the label, which is like a type in a property graph, that the code, the iCal code, the name of it, the lat long kinds of things. So these are examples of attributes that you might want to store in a graph. And then on the right-hand side, you can see an edge, and you can see examples of the edge that you want to have there. And so you have the edge has an ID, it also has a label, and in this case, the edge has an attribute called distance.
So I actually have a question here. So I'm a huge graph nerd. And so when I look at these properties, they're kind of non-directional. Like the route, regardless of which way you're going, would have, at least in this example, I know planes take different routes sometimes, but same amount of miles, the label and the ID would be the same. Now here in this diagram, we have directionality for those edges, where it's, the arrow has a head on one side rather than it being a bidirectional relationship. Obviously, depending on what data you're modeling, directionality may or may not be important. But how does that work with respect to the property graph for the edges? Or is that like something that is
and so in Neptune and in property graph and RDF, the edges are directional. Mm-hmm. So when you create an edge, you have a couple things that are required. So you have to have an identifier. This is in property graph. You have to have a label, which gives it a type in property graph. Then you have to have a to and a from node. Mm-hmm. So where is the edge going to, and where is it coming from? And in the case of property graph, those nodes and edges have to exist the nodes have to exist before you can create the edge.
Awesome. Yeah. Because I guess maybe even when you're designing your graph data set or your model, essentially, there may be relationships you want in one direction that you don't need modeled in the reverse direction, and you'll only know that depending on how you're thinking of querying or the data that you have at hand.
Right, and you could always traverse the each edge in the backwards direction if you choose. Right, and so it also, whether things are modeled as an edge or a node, as I mentioned earlier, can really become a design choice. I mean, I think often the example that people often think about is a purchase order kind of scenario. You start building an application and customers are buying things, and you have a node from customer purchase product, and then you realize that they buy many things at one time, and you want to track it. And so then you think about a purchase order as a node, and you go through those kinds of scenarios.
Awesome. So we have what this looks like. We have our entities, which again are the nodes and the edges, or the vertexes and the edges. But what does it look like to try and query or to assess this sort of model?
Yeah, so one thing before we get to that, let's take a quick look at what it might look like in SQL.
Yeah.
So prior to graph querying, this is what...
this is already like making me sick. This is what the sneeze was for. Sorry, I've worked in a lot of different places where we've tried to model this sort of stuff in SQL, and I've been the DBA. I was volun drafted into the role. And when you have this r.from stuff, no, I'm not ever managing that ever again.
Yeah, I mean, so you absolutely can model these things in a relational database or key value store, for that matter.
I mean, we used to have TitanDB was a thing that you could run on DynamoDB, and it would do that same sort of setup as here, as you would have these from and to, and you would have things represented in these different fashions, and so it does work in key value stores as well.
Yeah, I think the challenge is that one thing is when you want to query this data, when you want to ask that question, like what are the routes between Austin and Auckland and how long are they? You end up with a SQL join query kind of like this, because the way that you traverse these relationships in a relational database is through joins. And that has obviously the pain of writing these large join queries, but it also has a performance implication in that the kinds of I/O access patterns that tend to occur in graph databases are very different than relational databases are optimized for. So these join queries are not only difficult to write, but they tend to execute slowly. And so you have this sort of double whammy, if you will, of something that's hard to write and maintain, and then something that's kind of run slowly.
And the maintain part, I feel, is one of the least... People forget that someone after you is going to have to look at this code. And someone after you is going to have to eventually modify this code. And if that person knows where you live and they're looking at a query like this, you're not safe. So it's really important, I think, to frankly, I think there's a better way of writing this query.
Sure.
But the fact is, you shouldn't have to contort your mind into some fashion that can write these queries, because you're going to have to train anyone who comes after you to do the same thing.
Yeah, and I think the thing that just like gut reaction is we can formulate a question that's so simple, right? What are all of the users that flew between these routes, or what are all of the cities in between this start and end destination? These are simple questions with what should be very clear one-step answers. But here you have to write a query that you are reverse engineering essentially how to ask that question in your tool's format or syntax, rather than simply having a tool that can operate the way your brain is operating. And so that may have been a limitation of technology at a certain point in time, but that was never a limitation of what could be possible with respect to creating a querying interface. But even today, people still write queries like this, right?
Sure, and one of the things that we talk about is if you're in a room with and you're asked to solve a hard problem, typically people get together, they have a discussion, and then somebody goes to the whiteboard and they draw out, this is going to be connected to that, it's going to be connected to that, and then there's going to be this thing that happens, and then we're going to go there. And so they solve the problems by conceptualizing it as a graph on the board. And then we go off and build, build it in a relational database or build it in a key value store. And that's not always the wrong choice. It's just, it's if the key part of the problem is traversing these relationships, then graph can give you both better development velocity, so faster time to market. And the thing that I think is also underappreciated is that when you do these kinds of things over relational key value, you have to denormalize your data because of this performance problem. And you can get better performance, but it ultimately costs you in agility and flexibility.
Right.
Because the real power of graphs is, I can now just, boom, I want to create a relationship, I can do it. I can do it in the data model, it's very easy. The graph database takes care of indexing it for you and making it fast to traverse. And so you lose that when that agility when you end up having to denormalize your data.
You talk about denormalizing the data, and it's like you do have to do that to get the performance. And if you're not doing that, you're doing it anyway without realizing it, because what the engine in the background is doing is it's creating some view, and then creating a B tree on that view that you're querying, because you query it so often that the optimizer goes in and says, hey, stop joining these tables. If you run explain on the query, it's like you need indexes on every field. You need foreign key constraints on everything.
Or, like if you're just trying to go through a full database, you may just be doing scans, like just completely unoptimal. But I think, honestly, it's like you shouldn't have to feel like you need to relearn how to think about how data exists or how you're asking questions. But to do that here, not only do you have to rethink how you're asking the question based on how it's formatted, but there is some sort of skill floor where you have to learn all of these different parameters just to do the thing you already know you want to do, right?
Honestly, the way most people learn it is they build this in a relational database the first time, and then they hit the performance wall, and they're like, oh crap, what are my options? And then they Google graph database, and then lo and behold.
Or they watch this show.
Or they
hear about it the first time, so they don't have to learn from their mistakes. They can learn from other people's mistakes or history, whichever you'd prefer.
So let's see what this looks like in Gremlin.
Yeah, absolutely. So one option that we have with Neptune is you can write it in Gremlin. Now, Gremlin is an imperative traversal language. It's something that's in open source, part of the Apache Tinkerpop project. And so when you write in Gremlin, you can write these traversals directly that look at the nodes. So here I start with I say g.v has code Austin. So now I've just basically looked up all of the vertices that have this property AUS, which is an airport code in this case. And then I traverse the edge label route, and I count them. And that's how straightforward it is to basically count all of the outbound edges of a label route coming from the airport in Austin. And so you can sort of see that the graph optimized language makes it easier to traverse and write. Now, it's not always familiar. If you're used to writing SQL, this may not look like something that immediately is there. But I think as customers use it and try it out, it's certainly they come to appreciate the value of being able to traverse and address these relationships directly.
One of the things that took me a long time to kind of grok with the language was dedupe and stuff like that. Is your own node can be included in your queries. So you start from a particular node, or you start from like the root of the graph or something, and you go and you write some query that says, hey, find me all of the paths that have the following attribute. And then I want you to find some mapping out of those to get some other thing. And in SQL, that can happen too when you have these complex graphs. But in SQL, you have your node as like an ID that you've set. And in Gremlin, I forgot that you needed to like take out part of the query of what you were querying, if that makes any sense. That's not a good explanation.
I mean, Gremlin does have a dedupe, traversal step built into language, and it is something that there's lots of things that can happen in graphs. So you can have cycles in graphs.
Exactly.
So where edges point back to themselves, or where they go through other edges.
Directionality and Hamiltonian graphs and all of these other wonderful things.
And it's also shockingly easy to write a Gremlin traversal or a Sparkle traversal that brings back the whole graph.
Yeah.
Right. And so there's lots of those things that it is optimized for graph, but there's still some lessons and tips to learn around the way. I mean, I've seen it in Gremlin, and I've also seen it in Sparkle. In some places people make a spelling mistake on a variable, and much like forgetting a where clause, it brings back a lot more than you expected.
Yep. And I've learned that now, and I feel like after a couple days with Gremlin, I have a pretty good handle on it, because there are only so many verbs that you need to learn. There are only so many parts of the language that you need to learn, and then with that simple toolkit, you can go out and write just about anything.
Mm-hmm.
So
absolutely.
I like it as a language. I much prefer it over Sparkle.
I think there's important use cases for both, and I think that it does come down to preference. I mean, and people do feel passionate about it. But I think obviously you're on one side here, but I think what we really see is for regardless of the passion for Gremlin or the passion for RDF and Sparkle, people are really passionate about graph.
Yeah.
And like that's really where we want people to focus is, what is it that you need to build graph applications, quickly and effectively? And part of supporting both models was very intentional for that reason, because we saw customers that wanted RDF and Sparkle, we saw customers that wanted Tinkerpop and Gremlin, and in general, we saw customers that wanted graph. And so we wanted to, give them the tools to do that.
And to speak a little further to that, I think it's something on the order of 95% of AWS's feature roadmap is customer driven. And so when we say we saw customers wanting this out in the wild, that's from existing customers we speak with at meetups, at our conferences, summits, so on and so forth. Talking to us is the best way to guarantee that features or compatibility for certain languages will make its way into production, because we're building for you at the end of the day.
And this episode is a great way to get Brad to implement things. So
talking directly to the person who helps drive that feature roadmap.
With video evidence, for sure.
Yeah. You're committed. So maybe we could take a look now at a Sparkle query or kind of dive deeper on a couple more use cases. We've only got about 15 minutes left, and we're going to have to get to some questions at the end. So let's see if we can't show a little bit more of Neptune and talk a little bit more about it, and then hop over to the questions.
Yeah, so let me take you through another graph query example. And so I'm just going to brush over, so there's the oldest and most well-known graph benchmark is something called the Lehigh University benchmark, or the Lubin benchmark. And it basically consists of it's a parameterized benchmark. It consists of universities, where universities have students, and they have professors, and professors teach courses, and students take courses, and away we go.
The traditional university structure.
The things that used to happen at a university, right?
Where teachers teach, or students teach the courses, and teachers are learning from them.
And so this query has, this benchmark has 14 different queries, and they basically ask different questions about this data set, and it's designed to evaluate, graph databases and graph database performance. And this happens to be Lubin query number 2, which effectively asks, find all the graduate students that are taking or doing their graduate work at the same university where they did their undergraduate degree, essentially. And we can look at this query as a conjunctive join, and here's the screen is showing sort of what that pattern looks like. So I want graduate students that are members of departments, and departments are part of universities, and then they receive their undergraduate degree.
Okay.
So let's then look at this query now, first looking at in Gremlin. So, imperative traversal, we start off, find me all the graduate students. We store it off as student in a temporary variable we're going to refer to later. And then we start traversing the relationship. So find me this outgoing edge where the graduate student received their undergraduate degree. And then find the vertex there, and then find the incoming edge for where the departments are suborganizations of the university. And then go back to the graduate students that are members of those departments, and then effectively, take the intersection of that set with the where clause, referring back to the student. And that's effectively how you would evaluate that question in Gremlin.
So you're kind of saying, at each step of this query, you're saying, get me all the data coming out of it, and then you're filtering all of those. Get me all the vertices coming out that have this edge. Get me all of the vertices that are going out that have this edge, and you're kind of going and filtering at each step of the query. And
that's right. And then you're comparing that filtered set, which is where the graduate. So you start and get all the universities where all the graduate students got their undergraduate degrees, and then you take the set of the students there, and with the universities that they got the graduate student from, and then that's effectively how you reduce it.
So it's like a giant old Venn diagram.
Yeah, and you're traversing along the way, and that's really how the imperative traversal languages work. You're building this traversal as you go.
And if you were to try to imagine what this looks like, if you take the first one where they're all graduate students, you start at that pool or all of those nodes, and with each of these steps, you could iteratively try to imagine sort of what new nodes are lighting up that satisfy those relationship as you go down. But I think the most important part here is that you don't have to figure out what the transform necessarily is, like with joins in SQL. You really just have to understand, okay, what is the sequential order of parameters, essentially, or properties that I need to know and enumerate such that Gremlin can return the set that I want. Right. And it helps distill that down as simply as possible.
You just need to know the relationship or the edge you want to traverse. You don't even need to know the type. You could say any edge. You could say find me, in this case we're asking for something specific, but I could say find me graduate students with any relationship. And so you don't have to really know a deeper level about the data model there.
There's a joke in there about graduate students and relationships being non-existent.
Yeah, we may take that offline, perhaps.
Everyone's too busy to.
Yeah. So we can also ask and answer the same question using Sparkle. Now, if you're familiar with SQL, Sparkle is a declarative graph query language, like SQL is a declarative query language, and so to look a little bit more familiar from that perspective, you'll
a
notice
little bit worse.
you'll notice right across the top that the IRIs that I mentioned. So you see these things that look like URL. Those are IRIs. That's where you're getting this strong sense of identity that is very powerful for a lot of these applications where you're merging data or joining data together.
And I see it has this OWL reference, which was the ontology that you were talking about.
Yeah, so OWL, the ontology web language, that's the W3C standard that I referenced earlier, and which lets you effectively apply different levels of meaning over on top of your data. And then to evaluate the query, we're going to do this select statement. And so we're basically going to select student. And in Sparkle, variables have this question mark name is how you refer to a variable. And we're going to do it in a where clause. And the first three, what they call triple patterns, each one of these lines represents a triple pattern, basically bind the variables to different types. And so students bind all of the graduate students to the student variable, bind all of the universities to the university variable, bind all the departments to the department variable. And then we execute the conjunctive join. So now, in this case, here's where we're traversing, basically. So we're looking for this pattern where students are members of the departments are sub-organizations of the university, and then the students receive their undergraduate degree from the same university. And those shared variables between the triple patterns are effectively how you execute the joins and how you traverse it.
So the first part of this is basically setting up the query, setting up the variables that we're going to use by loading them in from this common RDF type. So we're saying that the type is going to be brought in from this ontology from the whatever the university benchmark is, and that's going to be bound to like an RDF type, and then we're going to use the edges from like this ontology again, member of. We're going to use the edges sub-organization of, and edges undergraduate degree from.
Yeah, and in this case, and that's true in this case, but really really this student RDF type graduate student is really just expressing another relationship. It's saying that this variable student has this relationship type to this other node that's graduate student.
All right, can we go back? We have a question from the stream from Pollos Hernandez.
Yeah.
Sure.
So if we go back to the Gremlin query, the question is just what is the string that the student is being compared to? And it's not that it's a string that it's being compared to, right?
Yeah, think of it as the as in Gremlin is effectively like sort of storing it off in a buffer. So basically, take the result of this step in the traversal, and I want to take that effectively net name solution set. I want to call it student, and I'm going to later in my traversal refer to this thing student, and it will have the value that was evaluated at the step previously.
So we're saying at the top here, this vertex graduate student is being stored as student, and then we're doing the where clause at the end here and the equality match of find me all the students that match these conditions.
Yeah, and it's not just a graduate student, it's
the set,
all of the vertices that have the label graduate student in the graph.
So in the beginning, essentially, and correct me if I'm wrong here, you are instantiating this variable or data structure student that represents the entirety of this, the output of the first query here, which is all graduate students. And then all of the other steps are going to be filters or transforms on that student graph.
Well, they're not even it's not a filter per se. It's taking all of the vertices, all the nodes, and it's just storing that step in the traversal off. And then we continue. So we say, find me all the graduate students, store them off. Now, find me all the outcoming edges from all of the graduate students. So we're gonna do traversals on that. And it's not until the end that we take the intersection with all the graduate students, with all of the ones that we've gotten to with students where they got their undergraduate degree.
Great. All right, let's talk a little bit about Neptune very quickly, and then we'll hop over and do a couple questions from our email.
Of course.
So I think you have a slide kind of walking through what Neptune looks like.
I do. Let me just get back there. So this is a very, this is our architectural diagram, if you will, of Neptune. The core of Neptune, which is that sort of blue rectangle, is a purpose-built storage engine that's optimized for graph and is durable and acid with immediate consistency on the write master. And then we expose that functionality by supporting both property graph through the Apache Tinkerpop and Gremlin stack. So every Neptune instance supports a Gremlin WebSocket server and a Gremlin REST server. And then we also support the RDF graphs and the Sparkle stack. So every Neptune instance also has a REST service that implements the Sparkle 1.1 protocol. And so that purpose-built engine is exposed to you in open source and open standards ways for you to use your graph. Now, all of this sits on top of a cloud-native storage layer that was originally developed for other AWS database services, and it provides multi-AZ high availability. We support up to 15 different low latency read replicas. We support encryption at rest with customer manager.
Sounds
KMS
mighty
keys.
familiar.
It's definitely a key. It's a very differentiating technology for databases.
And a lot of the things and topics and services we've discussed in previous episodes are not just generalizable to just SQL, just NoSQL, or now just graph databases. It's how does the offering here in Neptune build upon the general graph best practices and principles with all of the knowledge we've built to be able to build a product that can truly be cloud native and cloud first. And that intersection is what Neptune essentially is.
I mean, I think one of the things, I was talking really earlier about, how it's exciting to be in graph today, but, the fully managed aspect of Neptune is really a differentiating piece for a lot of customers. I mean, graph databases can be difficult to manage. You spend a lot of time with JVM parameters. You can spend a lot of time trying to create custom indices. And part of what Neptune does is give you a fully managed experience for provisioning Neptune. High availability is available, and if you choose the smallest or the largest instance, you have a highly available cluster. And so I think that's one of the things that customers use to build graph applications with confidence
Right.
on top of it.
So one of the things that I like about RDS in general is that it manages a lot of things for you. Like you're talking about this fully managed solution. You get your backups, you get patching and all these other things. However, in RDS, we have this concept of parameter groups that you can use to apply specific parameters to the underlying database engine. Do we do that at all in Neptune, or do you just don't even need to care because it's all kind of managed?
Neptune does support a similar concept
Okay.
to parameter groups.
Cool.
I think that one of the things that we've done as a product from a product design philosophy is we've tried to give customers as few knobs and dials as possible.
Sensible defaults.
We want to, you can choose options like controlling your query timeout. There's a few other different options, but in general, they're really related to deployment pieces and things for managing the instances. And we've really tried to make it easy for you to load data and have a good experience and good query performance related to it.
So you don't want to be tinkering, you want to be tinker popping.
You want to tinker with your graph, not your database instance, right?
Yeah.
That's the tagline for today's episode.
I've just been waiting to make that pun the whole time. So, all right. So this is Neptune, and it's generally available now as of like May.
So
2018.
Neptune, we just had our first birthday. The cake is a couple weeks old, but I'd share a piece with you if you want it.
It's distributed in graph format across all the people that ate it already.
And we're now launched, in 11 regions worldwide, and so we're continuing to expand the service. And we're always launching new features. So, for example, just today we're going to be announcing the ability to put audit logs in CloudWatch.
Nice.
And we launched in the sort of Seoul region last month, and so we're continuing to to increase and and make updates to the service. So.
And I think one of the things that kind of prevented you from getting into Seoul was they had to add that additional availability zone. So both Seoul and one other region recently added an additional availability zone, giving them 3 availability zones. And the way the storage engine is designed is like it wants the data in 6 different copies and 3 different AZs.
And backed by S3.
Yeah.
Right, 11 nines of durability.
And
right.
and so I really loved seeing some of the older regions get that additional availability zone so that they can kind of immediately, I've seen this rush of all these services coming in and like deploying into those regions since that's happened. And now we've got, I think, 21 regions with 66 availability zones, which is pretty darn cool. It's a lot of places to deploy. All right, cool. We've got time for 2 questions from the stream, from the database email. So the first question that I have is from Doron Lavari, which says, how can I maintain multiple similar identical schemas or databases in the same database service? I think people understand how it's done with Aurora and DocumentDB, but everybody would be fairly interested in knowing how it's possible with Neptune and maybe Dynamo. Did we already answer this in the last?
Yeah, so we talked about it with respect to Aurora serverless last time. But I think with respect to Graph and in Neptune, do we want to speak to that a little bit? Like, what would different schemas essentially look like for one data set in Neptune? Or would you even have multiple schemas for your same data set?
Yeah, so today in Neptune, each cluster effectively gives you a graph that you can use for your property graph in Gremlin, and then you have the RDF graph that you can use. And within that, within your application, you can have many different graphs that would coexist inside of there. We don't today in Neptune support a kind of multi-tenancy concept where
Right.
you could have multiple databases within a single cluster instance. So what we recommend in that case is to have more smaller clusters for that.
And the idea of kind of taking multiple places, that's what Sparkle is you have those IRIs, so then you can...
Yeah, and in the Sparkle use case, there's something called a named graph, which serves as a container concept. So many customers will build applications using named graphs as the container for it.
And then there was a question from the email about a kind of Active Directory relationships and things like that. How does that go with Neptune, or is there no integration?
So
Sorry, we are running right up against the clock, and there's another stream that is coming immediately after us, like right now. So that's all the time we have for today, unfortunately. We will answer this question off stream and get that responded to. But thank you so much for coming out. This was, again, our episode on Amazon Neptune and graph databases. So thank you again, Brad. It's been a pleasure.
thanks a lot.
Thanks for coming on, Brad.
Appreciate it. Thanks
We'll see you
everybody.
next week.